Now, you've already seen there's a bunch of ways of dealing with state machines. In this video, I'm trying to look at one of the more sophisticated approaches towards handling state machines, and that is the state pattern. Now, you may have already heard from the Gang of Four. These are four like super programmers, like heroes of their discipline, and they formulated the state pattern like this. Now, the state pattern allows an object to alter its behavior when its internal state changes. The object will appear to change its class too. Now, like most very abstract and common definitions, this isn't saying much. So let's try to look at it a little bit more in depth to really understand what this design pattern is actually about. So the state pattern is a design pattern to create a state machine. Now, what is a design pattern? If you're not familiar with the term, it's just basically a very, very good solution for a very common problem. And in this case, the Gang of Four would describe it as a go-to solution for implementing a state machine. Now, the state pattern tries to encapsulate the states so they are no longer coupled to the enemy itself, for example. So what this means is, right now, we hard-coded all the states the enemy can have into the enemy itself. And this comes with a few disadvantages. For example, due to the fact that they are implemented into the, for example, turtle enemy, you can't necessarily reuse them for another enemy. So that's one of the huge disadvantages with the approach that we tried up until now. However, this design pattern aims at this flaw and tries to fix it. So one of the goals of this design pattern is to make the states reusable. However, not necessarily completely reusable. So you can reuse like a whole state machine and make it so another enemy uses the same state machine. It seems like a huge advantage, and it might be for big projects. For small projects, it's not that important, to be honest. However, if you have like 7 enemies that behave in the same or a very similar way, it will definitely be worth it to implement the state pattern. Now let's look at what this means in a practical example. Now, instead of having an enum which determines the state, we use a separate class for each state. For example, we use the run toward state or the run away state and extract them into a separate class like runaway.cs or runtoward.cs. So every state needs to be completely independent. That's very important. If you're familiar with the principles of object-oriented programming, you surely have heard of the term encapsulation, and that it's very good to encapsulate your stuff so it's not as tightly coupled to other classes, which is usually like a sign that your code has a high quality. And thus, it would be very beneficial if each state is independent of, for example, the enemy it's put on. That's a huge advantage, but it also comes with work, so it takes quite some time and adds some complexity to your project. So it's not just great and beneficial, it also comes with a cost. So for big projects, this cost is usually paid because in the long term it pays for itself. However, if you are developing a very small game with, 3 enemies with 5 states each, it might not be worth it to invest so much time into creating this state pattern. Now, let's look at a practical example, what this means. Now, I have an enemy AI. This enemy AI references a state machine, and this state machine can have one single state at a time, but it can switch between these states. So it can be in the run towards state, run away state, or the idle state. And each of these states is a whole script, or at least a whole class. So they are completely independent and separated. You can then use a second, completely different enemy who has also a state machine and reference the same state. So you can reuse the state machine. That's basically one of the advantages of this design pattern. So let's dive into the code. First, we need an abstract state class. Now we don't use enums anymore. So instead we're going to define an abstract state class. This abstract keyword, if you're not familiar with it, it just means that this state cannot be instantiated directly. You first have to create another state which inherits it in order to instantiate this state. For example, you could create a follow state which inherits this abstract state class, and that would work. We'll see why we're doing this right away, but for now, let's just look at what's in there. So we need a game object, the game object which has this state basically, and a state machine which assigns the state. You need the state machine to change the state, so to create transitions. And you're going to need the game object which this state is on, because usually you, for example, want to move the enemy. So that way you can just use this game object reference and get the transform component from this object. All right. So also you should note that this is a common C# class. It's not a mono behavior. It's a common C# class. Okay, what's next? Here we have the constructor. I know it's rather rare seeing these in Unity, but the better you get in programming with Unity, the more you realize that you shouldn't use too much mono behaviors and that you should try to not use them whenever possible, because it saves performance. Okay, so in the constructor, we just set these. Right, now let's get to the interesting part. We have 4 methods. You can expand this, okay? But these 4 methods I think are rather important. Now we have the enter method. This is called when this state is entered. So if the state machine switches the state, this enter method is called. And you can set the state up. You can, for example, change the color of the game object in order to mark it as being in the following state or whatever. Then we have the update method. This update method should be called when the Unity update method also is called. So we are going to call this update method from our enemy, okay? The same we're going to do with the fixed update, because in the fixed update, we're doing physics updates. In the normal update, we might do something like detecting if there's input to read and to react to it. And then we have the exit method, which is called when the state is left and another state is entered. Right. Now, let's get one step in the hierarchy up. So now we're looking at the state machine itself. Now you can already see that the state machine contains a state. So it has a reference to one state. And then I also created this property here, which is a getter and a setter. And in the setter, I need to do something. So right here, I just say if there's a state already in there, we need to call the exit method of that state. So this method. We need to call all of those manually because it's just a regular C# class. So that way it can, like clean up after itself. Next, we set the current state to the new value. And lastly, we also say that the new state should call the enter method of itself. So that way the old state cleans up after itself and the new state sets up its initial stuff. Right, so that's really the primary thing the state machine itself is for. Now, coming up next is the class that actually uses the state machine. For example, the enemy. Now, the enemy, of course, needs to have a reference to a state machine. We just create a new one here, and then we set the current state to one of these specific states. For example, the chasing state or a fleeing state or whatever. Do note, it needs to be a state which derives from this abstract state class. All right? Good. And we tell it which game object it's on, and we also provide it with the state machine so it can change the state on itself. Next, we also tell it if the update method of the game object which this state lies upon is called, it should also call the update method of the state. And the same goes for the fixed update. Now you can also improve this a little bit and expand upon it. You might also need to call, for example, the onTriggerEnter or the onCollisionEnter methods, which lets your states react to collisions. I left this out for now because it didn't fit into the slide. So feel free to just expand upon this approach. Now, let's compare the state pattern with a simple state machine. Firstly, in the state pattern, the states are completely encapsulated. In a simple state machine, they're not. Things are tightly coupled, you know? Each state is coupled completely to the enemy itself, for example, and you can't reuse it in another enemy. Second, states can inherit one another. You can, for example, create a move state and then create some specific move states where they move slightly different. So that's another benefit if you have like similar movement patterns or something. In the simple state machine, states can't inherit. There are no classes, so that's also a downside here. Also, in the state pattern, you can reuse the states because you just need to create another enemy with another state machine and just give it the same states. That's absolutely no problem. When you create a simple state machine, like we saw in the previous videos, it's not as easy. You can do it, but not by default. I mean, you have to work around a little bit. It's possible, but yeah. So let's look at the disadvantages of the state pattern. Now, firstly, states can't be changed easily in the inspector. As you saw in the previous videos, with a simple state machine, you could just choose the state of the enum with a drop-down box. State pattern uses classes, so that's not an option. Now you can work around this limitation by also creating an enum and then saying if this enum is selected, put this state class in there. Yeah, that's possible. But that also means that whenever you create a new state, you also have to update the enum. So it creates additional work. It's possible to adapt it, creates additional work. You shouldn't forget about that. Now, next, it also takes far longer to set the state pattern up. It's also far more complicated. You have to keep in mind far more things. So it's way more complex than the simple state machine that we saw earlier. And there are a few things you might miss out or just do wrong. So that's something to look out for. And yeah, the benefit, of course, of a simple state machine is that it's set up so fast. You can do it within minutes. Yeah, a state pattern needs to be set up probably at least half an hour, maybe an hour, depends on how fast you work and how complex your AI is. And lastly, one of the downsides of the state pattern is that you may need to create very many classes because each state needs a separate class. And that might also increase the compile times of your project. So be sure to just use appropriate namespaces to reduce compile time, at least slightly. All right. And of course, in a simple state machine, you definitely don't need to create any additional classes. So you're just faster. Good. However, the main benefit of the state pattern, as I already said, is that it's encapsulated and thus it's less coupled to the rest of your project. if you're working smart. All right, now that you know about the state pattern for yourself, I want to tell you a little bit about what I think about this pattern. Now, firstly, it works quite nice for big systems. For example, like game states for turn-based RPGs, where the buttons change what they do depending on the state of the game. A good example is if you have a few buttons and depending on it, if it's your turn or the enemy's turn, things change up a little bit. So that's where this state pattern might come in quite nice, I think. However, I don't think it works very well with a small scale AI. So with just a few states and a few transitions, this state pattern is probably a huge overkill there. And the problem that I have is if you have medium or large scale AI stuff, I mean, the state pattern makes state machines better, no doubt about that. However, there are better solutions to AI than using the state pattern. At least I feel that way. So what I usually use instead is a behavior tree. And that's why I don't find the niche of the state pattern between like small scale AI and medium or large scale AI. So I'm not using them too frequently, but as I already said, I mean, they have their parts and some people really love them. So it's a good thing to know the pattern and to recognize it when you see it in the code of a colleague of yours. So for my rule of thumb is if I have an easy AI with up to 5 states, I use a simple state machine, code it all in the enemy itself. And if the AI is more complex with many states and transitions, I usually just use a behavior tree because that scales up extremely well compared to a normal state machine, at least. You keep in mind, you can also combine a behavior tree and the state machine, but we may look into that in another video. Now, that's really it with the theory of the state pattern. It's quite a bit. If you didn't see the code or didn't write the code, it might not immediately click so you understand what it does. And that's why we're immediately going to look at a practical example where I implement a state pattern in a catch game. So I'll see you in the next video.